All right, so today we're going to at least start chapter seven, which is the second last chapter in the course, by the way. We still have eight to go. Eight is our discussion about what are called confidence intervals. But here we're going to actually do an interesting application of the normal distribution. We're going to introduce something called sampling distributions. So what exactly is this all about? Well, let me just quickly remind you that when we are analyzing data, we usually have to use a sample because populations are usually very large, and gathering all the information we need would be very time consuming and possibly costly. So we end up using a series of sample measures to represent the underlying population measures. So for example, X bar is used to estimate um, or as an estimate of mu. Of course, this is the sample mean. And this is the population mean. And again, if you remember, the convention is that we use the Greek letters for populations and the Roman alphabet, which is our alphabet, for sample measures. So in addition to that, there's a few others that we know. For example, S squared. Squared is used to estimate sigma squared. Of course, that would be the sample variance. You can tell again because it's S, and over here it's the population variance because that is the lowercase Greek letter sigma. And of course, S is used to estimate sigma, just plain sigma without the square. This would be our sample standard deviation. That, of course, means must be the population standard deviation. So the measures that are used to represent a sample are referred to as sample measures, of course, or sometimes they're called sample statistics. Right? That word statistics indicates that this is a sample measure. The corresponding population parameters, as they're called, would be, of course, mu, sigma squared, and sigma. Okay, now what is this chapter all about? Well, think about the following situation. Suppose that a sample is chosen from a population. So let's think of a specific example. Imagine a researcher goes to a mall and asks the passersby how old they were. It seems like an odd question, but let's just say he's doing a survey for some reason, and maybe he's asking about other things too. But the bottom line is he's going to say, "Listen, we're doing a survey about this, or that product, and what is your age?" They usually want to know some of the demographic details when you do a survey, and so it's not that unusual that they would ask you for your age, especially if it's a product that you have to be an adult to buy. But let's just assume that this is what's happening. So now, obviously, the population of interest is enormous. So these samples are very important. And so let's just say that the researcher chooses a sample of 50 and determines that the sample mean is 29 years old. Okay, the average person in that sample was 29. Now, what if they do this a second time? The researcher chooses a second sample. And by the way, it's understood that this is a different sample. We didn't just ask the same people the same question. We have other people walking around and we just pick 50 other people. Now, here's the interesting question. will it have the same sample mean? And of course, the answer is no, except by an amazing coincidence. And let's say this time you determine the sample mean is, let's say, 35. So this one is a slightly older group. And then he does it again and again and again and again. If the researcher um, chooses enough samples, the results can be summarized in a histogram. And let's say this is what it looks like. All right, and so for this first one, we'll have ranges. Okay, now I'm going to run out of space, so I'll just let it, let me just fix this a little bit. There, that's better. All right. Let's just add a few more categories here. And then at the end, I guess we'll call it 60 plus or something like that. And so let's just say that this is what we end up with. Okay, so that's our histogram. Now, what we have here is a frequency distribution, but um, by doing this, by choosing samples and computing sample means, the resulting sample means will form what's called a sampling distribution. This is a special type of probability distribution where the results do not represent an actual population of some kind. Or another, what I'm saying is that it doesn't show the entire population directly. Let me put it this way: the results are derived from sample means. Okay, so what this is showing us is that most of the samples had a mean between 30 and 39. And then quite a few of them were between 20 and 29, and then it falls off on either side. So overwhelmingly, well, not overwhelmingly, but the majority of the people that were interviewed that day were somewhere between 30 and 39. So anyway, and of course you could also do this with individual values, but then it would be quite a bit of data there. So this sampling distribution, as it turns out, and we're going to see how and why this is happening, for X bar follows the normal distribution under certain assumptions. Okay, in other words, if certain assumptions are met, and you can kind of see it looks like it's heading towards the normal distribution. It follows the normal distribution if certain assumptions are being met. That's kind of important because what this means is that we can use this information to compute probabilities for the means of samples for sample means. In other words, imagine I'm a researcher and I'm promoting a product that's really meant for people in their 50s, let's say. So what I could say something like this: what's the probability that if I choose a sample of people, the average age will be at least 50? Okay, that's kind of important for what I'm selling. I'm selling a product that normally is only bought by 50 years and up, let's say, whatever it is. Something that only people in that category can afford, maybe, or something that only they'd be interested in. So it kind of helps me figure out, the likelihood of this happening, and therefore maybe that'll help me to decide maybe which age group I should be promoting my projects to or my products. But anyway, the bottom line here is that this distribution of sample means follows the normal distribution, which means we can calculate probabilities And it also means that this distribution has its own unique set of moments. Okay, so we'll say here that this distribution, the sampling distribution, has its own unique set of moments. Okay. So anyway, let's see how this works. So anyway, this is just background so you can see where we're going. So um, a few definitions that we've seen before. An element is what we're interested in analyzing. So in this case, the element would be ages. We're only interested in the ages of the people that we interview, not so much their incomes or their jobs or whatever, just their incomes. The population would be everybody, let's say in the United States. Not so much, I shouldn't say that, not everybody, but everybody's ages, because that's what we're studying. And as we know, a sample is a smaller portion of a population or subset. The sample population is a population from which we drew. Well, and I guess what they're saying here is that you can think of the people who live close enough to that mall to go there could be thought of as the population that we're choosing from, even though we're really looking at the entire country. And then a frame is list of the elements that we're going to choose. So we don't want to worry excessively about these definitions. We're not going to concern ourselves too much with these. What we do need to know is that, we're choosing samples. By the way, I do want to mention one more thing here. Sampling is a very complex part of statistics. There's many different ways to choose a sample from a population. And every discipline does it a little differently. Just as a quick example, for example, a psychologist might be interested in finding out if men and women have different attitudes about cars, let's say. I mean, it could be literally anything. So in that case, the samples would have to be chosen to ensure that each sample only contains men or women. In other words, you don't want a mixed bag because you're trying to figure out something about men and women. So you go out of your way, you'd have to find a way to make sure that you have samples of just men and another set of samples of just women so you can compare them to each other. Or another researcher may want to know if spending habits are different among different age groups. So then what he's got to do is pick out data so that each sample, let's say, only has 20-year-olds or 30-year-olds or 40-year-olds or something like that. So now for our purposes in business applications, we normally choose data in such a way that every element in the population is equally likely to be chosen. In other words, we're not interested in, let's say we're looking at ages. We're not making any distinction between men and women or, rich people and poor people or anything like that. Just everybody is one big group and we're only interested in looking at their ages. So everyone is equally likely to be chosen. And so that type of sample is known as a random sample. That's the norm with business applications because we want to know, for example, how much each household spends on cable TV every year or something like that. We're not overly concerned about whether they live in the, where they live or that kind of thing. We're just looking at the raw averages. That does make things a lot simpler for us, by the way. Because these other techniques do require their own unique sets of statistical methods to analyze them properly. So we're going to just stick with the old random samples here. Or imagine yourself doing financial research and you're looking at portfolios of stocks or something like that. You're going to randomly pick stocks for your portfolio and analyze their performance. Anyway, now we're going to make a distinction here between two different cases with sampling. Either the population of interest is what we're going to call finite. I'll put that word in quotes. You'll see why in a minute. The population of interest is infinite. Okay, now these words clearly aren't meant completely literally. What's this distinction between the two? The population is infinite, is finite rather, if it is not extremely large, let's say, compared with the size. Okay, so there's, for example, if a sample of 5 students is chosen from a class of 30, the population, the class that is only 6 times larger than the sample. So this would be considered to be, and you can express this in two different ways, a large sample or a finite population. On the other hand, if a sample of, let's say, oh, say 100 people is chosen from the entire population of the United States, which is at least 330 million the last time I checked. You could see that in this case, it's a little different because the population is massive compared to that sample size. So this would be an example of a small sample or an infinite population. Infinite meaning relative to the sample size. It's not literally infinite. It means infinite large. It's very large compared to the underlying sample. So that would make it an infinite population. Why are we distinguishing between these two? Because the formulas that we'll use will depend on which case we're looking at. Okay, the formulas will be slightly different depending on which we are choosing. Okay, so the actual cutoff point, well, we'll get to that in a minute. Also, a little bit of reminder here, in this book, we use lowercase n to be the sample size, and capital N is the population size. So here they're mentioning the simple random sample. And they're also going to introduce us to the notion of random numbers. Now, generating random numbers is a very complex process, but we have in Excel random number generator we can use. We're going to use this on the spreadsheet National League. So here are the teams, 15 of them. And what they're going to have us do is generate random numbers. So what they want us to do is this. We're going to generate random numbers and then use those to choose a sample. We're going to pick the 5 teams corresponding to the 5 smallest random numbers. So we come over here. And the Excel command is very strange. It's called rand, but you have to use open and close parentheses. You're not providing it with any information, just rand. Okay. And look what happens. I drag it down. There we go. And I can see the whole thing. Now, as it turns out, the Excel command ran. It has its good things and bad things. chooses a number from the standard uniform distribution. If you recall, that's the continuous version. Oh, actually, I should have made that in, put that in there, continuous. And that means it looks like this. So every number between 0 and 1 is equally likely to be chosen with this particular command. And if you notice, you look at them all and you see that they're all between 0 and 1, which is what they're supposed to be. Now, here's one of the quirky things about this, and I don't know why they designed it this way, but the Excel command brand has one strange feature. Updates itself every time the keyboard is used. So in other words, if you notice, every time you touch something on here, they change, and it's really annoying. So how do you get around that? You select the numbers, you hit Control C or Command C, depending on whether it's a Mac or a PC. Come over here, and then you're going to put paste special values and number formats. And so now the numbers we saw a second ago are locked in forever. They can't change anymore. These will keep changing, but these won't. In fact, you could delete this column if you want to. We don't need it anymore. So that is kind of annoying. All right. So let me remind you how this works. To prevent the random numbers from changing, copy numbers, use the paste special command with the option values and let me remind myself the exact way it's worded. Paste special values and number formats. Okay, so that's one of the quirky things you need to know about. Now, what they asked us to do, though, is organize them. They want to know what are the 5 smallest numbers. Those are going to be chosen for a random sample. So we're going to copy both columns. Now we can sort them from low to high by doing this. Oh, it's on the data tabs. Data, sort. Now make sure it says my data has headers. And then you ask it to sort by. Now there's no header here, so you'll have to tell it column E. And we want it to go from smallest to largest. So that means that these are the teams that we're going to choose for our sample. You know, there could be a lot of reasons why. Maybe Major League Baseball wants to find out, you know, how expensive food is at that stadium, what the average attendance is. There's a lot of reasons why they might choose this as a sample, but they want them to be completely randomly chosen. All right, they're not choosing the largest teams, the smallest, you know, the wealthiest, the most successful. It's just the first 5. With the understanding that whatever we find at these 5 stadiums is certainly going to reflect the rest of them. So if Colorado charges $8 for a hot dog, well, then maybe that's the price of the other stadiums. Or if they're trying to figure out how far it is to get to the stadium or how long you have to wait and all this and that. Okay, so that's a simple random sample in Excel, but be aware again that you have to copy and paste these numbers to prevent them from changing. That is a quirky thing. Now, there is, on the other hand, an Excel add-in that will let us get around this problem. If you wanted to, for example, generate random numbers, let's say in column G, without using that command, here's what you could do. You go to data analysis, random number generation. So the number of variables would be just the one. And let's say we want 20. Now the distribution for what we just did should be uniform between 0 and 1, but you can see we have others to choose from. And there it is. Oh, see, I moved it to another page. I guess I should have told it where to put them. And there you go. And if you notice, these are not changing. They're fixed constants. So you don't have to fool around with them. Now, this data analysis tool pack is something that we haven't really done much with, if anything. Though it's here, hiding on the data tab, has a lot of wonderful statistical packages built into it. But you do have to go through the formality of installing it before you get started. And that, unfortunately, is different on the PC and the Mac. So on the PC, if you don't have this showing up here, you have to come over here to File, Options, and then you want to go to Add-ins. And then you hit the Go button. And then you click on, there's really only two to choose from, Analysis Tool Pack and Euro Currency, no, sorry, Solver. So you pick the one you want and you hit OK, and all of a sudden you'll see them up here on your tab, your ribbon, I mean. If you're using a Mac, there's a special menu here called Tools, and one of the entries on that is, I believe, Data Analysis Tool Pack. And so that's how you would start this process. So look for Tools. You don't see that here. And on that menu, you should find what you need to install this Data Analysis Tool Pack. Now, you're not going to use it a lot here, but in Stats 2, you'll need it from time to time. It'll prove to be quite important in Stats 2. Here, we haven't really needed it so far, but it's good to know that it's there. And all right, well, anyway, so that's random numbers. Now, sometimes we are choosing from an infinite population, a very large population. So, oh, by the way, there's one more thing I forgot to mention here with the random samples. Everything I said is correct, but we're assuming that the elements themselves are chosen independently. So in other words, okay, I forgot where I put that. Oh, here it is. All right, I'll add this as a separate note. Note, it is assumed that all the elements in a random sample were chosen random, independently. So, I'm sorry, independently of each other. Now, imagine yourself asking people their age in the mall. If, let's say, a family of 5 walks up to you and you choose all 5 of them, that's not really independent. Okay, you pick them because they're all in the same family. No, it's just every individual who walks in that door is equally likely to be chosen, which means there's no connection between the choices. Okay. All right. Now, I think we're getting to our first problem here. Here's some more terminology. There's always going to be some terminology. All you really need to know here is that the word point means it's a single number. We're going to see something else in chapter 8, by the way. So, and also as far as the notation goes, let me just mention something here. So X bar, as you know, is used to estimate mu. And so distinction we make here is that X bar is a formula. It is said to be an estimator of mu, and since it's a single value, it is specifically known as a point estimator because of the fact that it's a single value. All right, so the word estimator is a formula. In this case, X bar, the formula, the sum of the X's over N. Once I find the actual numerical value, it's a result of calculating X bar, let's say is 3.2, then the terminology changes a little bit. 3.2 is now an estimate of mu, and specifically a point estimate because it's a single number. All right, so that's all you need to remember, the distinction between estimator and the estimate, and the fact that the point refers to the fact that it's a single number. That's really all this is about. We're not going to over concern ourselves with terminology. I don't think there's any questions about this on the final. All right, anyway, so here we go. So we've got employee data from this EAI company. We've got 2,500 employees, a single random sample of 30 is chosen. And it's going to show us, here's our spreadsheet for EAI. There's two variables here. Oh, by the way, the actual data set has more data than, see here, they can only fit so much onto this slide. So that's why they're telling us what happened with 30. We're going to get different numbers. And so annual salary, which is of course a numerical value, and training program, yes or no. Did they receive the management training program or did they not? So it looks like there's quite a bit of data here. Looks like 300. No, oh my God, they've really gone to town here. Man, that's a lot. Wow. Oh, oh, jeez. Well, this is a big data set. Let's just say, let me just, oh, 2,500. Okay, they did mention that in the slides, that there's 2,500 managers in this company. Okay. So we're not going to look at all 2,500, of course. In this case, they want us to pick a sample of 30. Okay, yeah, that is 30. In other words, you've got two columns each of 10. So therefore, there's 30 in this particular table. And of course, we're looking for, let's assume that we're looking for X bar. That is our sample statistic. And so they're going to have us do actually these. Actually, there's going to be three of them. We almost forgot about proportion. Remember how this, I should add that back to our list. Hold on one second. P bar is the sample proportion, which means what ratio of the elements have a certain characteristic. And P is the population proportion. So I'm going to go back and add that to our list. Remember in the beginning, I mentioned several statistics. sample proportion. Population proportion. That means P bar goes here and P goes here. All right, great. So that is another addition to our list. These are the ones that we know. Oh, there's plenty more, but we haven't seen them yet. You'll see that later on in stats two, or if you decide to, who knows, take statistics in a graduate program, you never know where you might go with this stuff. Usually when I say that aloud in a classroom, I get a lot of very interesting looks. It's like the students are thinking, what do you mean graduate school? Oh, that's right. That's what comes after college. Well, of course, that's optional, but it can add an awful lot of digits to your paycheck. Let me put it that way. But anyway, and it's also meant for specializing. In other words, going to graduate school means you've chosen a field that you want to specialize in, and that's all you're going to do for the entire program. And if you wanted to study statistics at the graduate level, it means you want to be a statistician and you'll only take stats courses. But anyway, that's way down the road. Don't worry about it now. So here, what we're going to do is they're going to ask us to calculate the basic sample statistics for this data. Now they're doing it with the formulas, but we've got Excel right in front of us, so we're going to use it. So first, I'm going to split the screen. So we've got so much data, we want to keep the headers visible. So you'll put split. Now, okay, it can split the screen in two different ways. Sometimes it doesn't work correctly. You can double check, double click, and let's try that again. I really want to split it from top to bottom, not left to right. See what I can do here. All right, that's much better. So you can get rid of this with double clicking. I'm only doing this so I can see the header. And then the bottom can go and scroll independently. It's very convenient when you have huge amounts of data. So let's try that. And it wants to know. Now, here's the mean. Oh, you know what I just realized? Oh, see, our numbers are not going to line up with these because they're referring to this particular sample that they've chosen. So we can't really do that here unless we go through and find out which one of these were chosen. We don't have time for that, but we know how to calculate these measures. As a matter of fact, these would be population measures anyway. So let's go past this right now. But on the other hand, I'll tell you what, why don't we try this? Maybe we could have a random sample. All right, I'll tell you what, let's keep this very simple. Let's just pick 10. All right, so we're going to need a number from 1 to 2,500 where they're all equally likely. So we're going to go to the data analysis tool pack. Oh, actually, I'm sorry, we don't need that, do we? I think there's an Excel command, rand between. Okay, there it is. Rand between, and then you can specify the highest and the lowest possible values. The only thing is I'm not sure if you can guarantee that they're all different. And notice how it's changing, which I don't like. So we know how to get around that. Copy, paste special. Numbers and values in number formats. And while we're at it, let's turn these into integers. We don't need these anymore. Now, that means what I have to do though is find these numbers. So like 282 is this one. Yeah, you can see even with a sample of 10, this is going to take a while. Um, yeah, I don't know if there's any way to speed this up, but okay, well, at least it illustrates what we're trying to do here. If you have the time, you could go through and pick all 10 of these, and then you would have your sample. And then you could calculate the sample mean, the sample variance, the sample standard deviation, the sample proportion. I'll tell you what, let's not do this right now. But you see what I had to do. Then I would go find 1956 and copy it here. Um, there's a way that Excel can do this for us, but I don't remember off the top of my head how it works. So we'll just leave it like this. But just so you get a sense of how you could do the sampling. All right. Anyway, let's get back to this. So they're going to have us, they're calculating the sample measures for this 30 set of 30 observations. And you notice how they're using that terminology, point estimator. And so they're showing us how the population measures are on the left. That represents all 2,500 managers. The one on the right is the corresponding sample means and standard deviation and proportion. And you notice they're not too far off. The standard deviation is a little bit further away, but they're not terrible estimates of the population measures. Now, if we do this again with a different sample, we'll get different numbers over here. And if we do this enough times, we'll be creating ourselves a sampling distribution. So now what about the moments? I did tell you before that this is a probability distribution that we're creating, so it'll have its own set of moments. So we have to be a little careful with these because we're referring not to the actual population, but the sampling distribution that we created. Um, so in other words, if we filled out this entire table, it would be itself a sampling distribution. You know what? I'll tell you what. It won't take that long. Let me just go ahead and fill this thing in. If I really hustle, man, if there wasn't so much data, this would be very much faster. All right, I'll tell you what, this won't take that long. I'd like to show you the way that we calculate the statistics. Um, 631. All right. 2407. Beautiful. 1188. 1943. Twenty 54. Um, well, since we're closer to it, I'll go do 2295 next. There's nothing that says I have to do these in the right order, but um, here we go. And then finally 791. Just way, way up here. Here we go. Okay, so that's our sampling distribution now. And if you wanted to, you could turn it into a histogram of some kind. But right now, what I'd like to focus on is the mean. Well, I guess we could put that here. Variance, standard deviation, and proportion. Okay, so the mean is simply the average. The variance, var dot s, remember, because it's a sample. The standard deviation, we could do this one of two ways, standard deviation dot s, or we could simply take the square root of the variance. The proportion is a little bit different. I don't believe Excel has a proportion. We're looking for the proportion of yeses. So what we can do is put equals count if. Oh, I think when you're dealing with letters, you have to use this count A. No, that I was thinking of something else. All right, now let's try this. Um, range is here. Criterion is equals yes. Uh-oh. It doesn't seem to like that. Oh, I know what the problem is. It doesn't want that equal sign. Okay, so 7 of them said yes. The total is obtained by putting count. If, I mean, obviously it's 10, but if you don't have that information, oh, see, that's the one that requires the A. That's what I was confused about. All right. So in other words, you see what I've done here? Count if says go through and count all the cases where it says yes. Count A, because it's not numerical data, but it's alphabetic data. Count A says go through and find all the cells where there's an entry. In other words, anything that's not blank. So that means there were 7 yeses out of 10. So our sample proportion is 0.7. Now, in the slides, they're telling us the population values. The first one is 71,800, not bad. They gave us the standard deviation of 4,000, not bad. And the proportion is 0.6, and we have 0.7. So even a sample of only 10 actually does a pretty good job of representing the entire population of 2,500. Wow. Okay. So now we can see how sampling is working and how we can use its results to understand what's going on in the entire population. And we also learned some cool new Excel commands. Actually, let me do one thing real fast here. Just so that we know what's what. Now, what they're going to do here, though, is introduce a series of moments for our sampling distribution. And so, remember how, by the way, I just want to point out here that X bar in this context can be thought of as not a single constant value, but a random variable. Okay, meaning that it has its own distribution and its own moments. So the expected value of X is written like this. It's also written like this, mu with a little subscript X bar. The variance is usually written with a subscript to distinguish it from the population variance. And of course, that means that this is the standard deviation of X bar. Now, there should be a formula for proportions too. Let me see what they've got. I think they expect us to do that one too. No, not yet at least. Huh, that's interesting. All right, well, anyway, well, just based on these. Now, the question becomes, how do you calculate these? So the first one is easy. So in other words, the sampling distribution has the same mean as the population. So let's see if I can draw a proper picture of this. And so the mean here is mu. Then we have some value sigma. On this side, oops, let me get that straight. The center of that distribution is the same as the population, but the difference, as you can see from the two, is that the standard deviation is much smaller for the sampling distribution. Or you can think of it the other way around. The standard deviation of the population is greater than the standard deviation of the sampling distribution of X bar. When you see the formulas, you'll understand why. The logic behind it is this. If you keep picking fairly large samples, the means will be closer to each other than if you pick small samples. Just as a quick example, if a researcher is choosing samples of size 5 and determining sample mean age for each sample, the sample means can be very different from each other. If he repeats this process with samples of size 50, sample means will be much closer to each other. Let me show you an example of this with Excel. So what I'm going to do is this. Let's go back to Excel. And I'm going to create, let's say, 10 samples. But each sample is only has only 5 elements. Okay, so what I'm going to do is use Excel's ran between. Let's say that the values have to be between 1 and 10. Now they changed. Now let me show you another way to stop this. I'm going to hit Control C right on the data without moving it. Paste special values and number formats. Problem solved. So you can see the numbers are somewhat different from each other. They're not radically different, but they're different. So now I'm going to do the same thing with, let's say, sizes, samples of size 20. So I'm still asking, I'm still going to have, oops, I'm still going to ask for numbers from 1 to 10. Okay, now I'm going to lock them into place. I'm just making these bold so you can see them, the headers and the labels very clearly. And now I'm going to have the mean or X bar. Oh, now wait a minute. What happened? They changed again, didn't they? I must have done something wrong. Hold on. All right, they're good. And then I somehow accidentally erased this one. So I'll just, okay, now we're good. All right, so the X bar is average. So, even without creating a histogram, it should be clear. Look at these numbers. They're all hovering right around 5, maybe 6. Up here, they're a little bit more volatile. They can be as little as 2 or as high as 7.8 and everything in between. If I were to now have as my sample size 50 or 100, these X bars would keep getting closer and closer and closer to each other. So, in those, if you could imagine drawing a histogram for each, it might look something like this. Now, the means should be the same. They're both hovering right around 6. In fact, if you calculate the average of the X bars, they should be very close to each other. Oh, what happened there? I didn't. There you go. Well, that's more like it. 5.14. Yeah, I mean, they're not that far apart. So, but the important thing is that here they're much closer to each other. So if you were to draw a histogram for these two cases, first with samples of 5, the histogram might look something like this. Whereas when I change that to 20, it would probably look more like this. All right. Now, of course, it's a very crude drawing, but I hope you get what I'm trying to get at here. The center is approximately the same, but what's really different is how spread out they are. Okay. So in the second case, the data, the mean is about the same. The standard deviation is lower, i.e., the data is less spread out. Anyway, all of that is to help us understand why the variance and standard deviation formulas are written the way they are. That's what this has all been a build up to. When you see these formulas, you might say, I don't get it. This makes sense. The sample means should be very close to the population mean, and they are. Okay, because it's the same data, but it's the variances where we have to watch it. And not only that, but as if that weren't enough, um, the standard deviation, we don't really need, we're not too overly worried about the variance. It's really the standard deviation that we need. So we'll focus our attention on that. Is smaller than the standard deviation, the underlying population that's already discussed. But in addition, its value depends on whether the sample is small or large. So that means we need two different formulas here. So let's do it in the same way as the slides. Now, by the way, and also don't forget the word small and large. I actually prefer that to what they're doing, but let me show you how this works. So this is a small sample or infinite population. This one is very similar. There's one extra term there. The difference between the two is this term. This is known as the, oops, finite population correction factor. And I just want to point out it is less than one. So what it's actually doing is reducing the size of the standard deviation. So that's how, now, how do you, by the way, how do you decide which is small and which is large? That comes from this formula. Oh, hold on. Infinite means this other one, finite. Now, what does that mean in English? On the left, the sample is no more than 5% of the population. On the right, the sample is more than 5% of the population. That's all it means. So you have to make that decision before you decide what to do about these two. Well, once you come to that decision, uh, all right, all right, okay, there we go. So that's how you decide which is which. So, all right, I think finally, um, we're this close to having an example. So, by the way, here, just as an aside, we're going to introduce the so-called central limit theorem. And this is a result in statistics that tells us when we can use the normal distribution for the sampling distribution of X bar. So according to this theorem, X bar is normal if one of two things is true. Number one, the underlying population is normal. Or, so it's, just to make it clear, it's one or the other. It doesn't have to be both. Sample size n, lowercase n, is at least 30. Okay. Now, if neither one of these is met, we need to do something different, which we will not discuss until the next chapter. But if we're choosing samples from a normal population, or the sample size is at least 30, then we're good. We can use the normal distribution. All right. Finally, let's see. I want to see what they're doing here. Suppose the director no, you know what? Let's try something different. I'm not sure how clear that example is. Let's try something else. Using the data from EAI, suppose that a random sample. Oh, by the way, in order to do this, I just remembered, we do need the population data. So I'm going to come over here and take care of that right now. All right. So I'm going to do this, the population measures equals average, B2 through B25. Okay. So this is the actual population number. The variance, remember in Excel, it's vr.p. The standard deviation, STDEV.p, remember it's a population, B2 through B25, just a hair under 4,000. And then the proportion, remember how we did that before? It's kind of C2 through C251, comma, yes, over count A, C2 through C2501. 60%. Okay, great. We're going to need those. That's why I'm doing this. Okay, so we're going to need, this is a different example on the right. This is something I just made up. For what we're about to do, I need these numbers. So we're going to say, in my example, suppose the random sample of 50 is chosen from the population. What is the probability the mean salary in the sample is between, let's say, 71,000 and 72,000? Great. So first of all, let's get our information back. So we have the population mean. So remember, the sample size is 50, the population mean is 2,500. We need the population standard deviation. And so to calculate a probability like this, what we're going to need to do is we need to know the mean of this distribution, which is 71,800. And then we need the standard deviation. Now for here, we need to determine if this is a large or small sample. All right, so remember the cutoff point for small is here. So here, all right, remember that's right up here somewhere. There it is. So that means what's the ratio of 50 over 2,500? That looks pretty small. 0.02, which is less than 0.05. That means this is a small sample. And if you look at the table we have up here, when we have a small sample, we're going to use this to calculate our sample standard deviation for X bar. So remember that standard deviation for the entire population is 3999.2. So, we can round this to two places. It's approximately 565.57. Well, now we're almost done because we can go to our Texas Instruments calculator and choose normal CDF. Okay. And then when we get there, of course, remember that we need to know the lower limit, upper, mean, and the standard deviation. But for this type of problem, this mu is actually the mean of the sampling distribution. But as it turns out, that's also the population mean, 71,800. This is the part that we provided. And remember, we got 565.57. Oops. All right. So now we just plug these in the way we always do, and we have our probability. Look how easy that was. All right, 71,000 up to 72,000. The mean is 71,800. The standard deviation is 565.57. It leaves me with 5596. All right. So all of that background was needed to get to this point, but once we get here, um, really all you have to do is make sure you make the right decision for the whether the sample is large or small, and you're in business. It's pretty straightforward. All the rest of this was interesting, but it was just designed to build us up to this point. Wow. Now, all that remains in this chapter is to do the same thing with the sample proportion. It has its own probability distribution, or I should say sampling distribution. Okay, so we need to know the measures that are associated with proportions, and it's very straightforward. Like with the X bar, the mean of the proportions is the same as the population, in this case, the population proportion. So we write this as P bar, okay? And then we have to make a decision. All right. So yeah, okay. It's the same thing. It's the same decision. But what's different is the formulas. Remember, small sample means infinite population. And large sample, of course, means finite population. So the formulas are here. Infinite is this one. And then if you notice the little p bar here, indicate that this refers to the sampling distribution of p bar, not the population standard deviation. And then the other one, there's that special term again. Coincidence? No. This is our finite population correction factor. So we use that just in case we have an unusually large sample, which means we have to correct for the standard deviation. Right, let's look at their example. Remember we were told the population proportion is 0.6, those who have the training. We figured that out ourselves in this spreadsheet. So they want to know if we took a sample of 30 employees, and remember the population is 2,500. So that ratio is 0.012, which is again less than 0.05. So this is once again a small sample. And that means that we're going to use this formula, the standard deviation. So Oh, so what they're doing is they want us to calculate the probability that it's within plus or minus 0.05. In other words, it's a roundabout way of saying, um, by the way, we have to be a little careful here because if you notice, P is being used to represent both probability and the population proportion. So just keep your eye on that. So anyway, we need the standard deviation. And let's plug that in. So it's 0.6, 1 minus 0.6. And we divide that by the sample size, which is 30. By the way, I do want to mention one more thing in passing. What we're doing here does actually have a couple of requirements. I kind of skipped over it, but I just want to show to you right now. You've got to make sure that before you do anything else with the proportions, this only applies to proportions. Let me just sneak this in here somewhere. Note that this only works if NP is at least 0.05. In this case, it's 30 times 0.6. Not 0.05, 5. And then it's the same thing has to be true for N times 1 minus P. Okay, so we're good here. And so we keep going. The standard deviation is 0.6 times 0.4 divided by 30 square root. That's about 0.089. That's close enough. So you're going to go to your calculator. And as before. Oh, by the way, one more thing. I want to mention this, that I'll add this at the bottom here. The distribution P bar is always normal, as long as these two conditions are met. Okay, so there's for this one, we don't have a separate central limit theorem for this. What it's saying is that if it's a proportion, and as long as those results hold, then we can justify using the normal distribution. If not, we have to use something a little bit different. Either that or the accuracy will suffer. All right, let's do this. Second vars, 2 normal, CDF, lower, upper, U sigma. Now, in this case, you're actually using this term. It says mu, I know, but it's EP bar. And then the standard deviation is this, which we just got through calculating to be 0.089. Which leaves us with it's about 0.4257. All right. Now theirs is a little different because of rounding. Plus they used Excel. But now there's these other, remember I mentioned before, besides random samples, simple random samples. Um, there's others too. I These are meant for other disciplines. I mentioned some of these before. I don't think we need to go through these right now because they're not going to appear on the test. But if you want to, you can go through and read about these other different kinds of sampling techniques. But I would say that we can definitely skip over this for our course. But it's there if you want to read up about it. Now, chapter 8 is coming up next, not in this session. The next session, we're going to wrap up chapter 8. What is chapter 8 about? Well, we're going to do something a little different. We're going to create, instead of a single estimate of a value, like for example, we know that X bar represents mu, but in chapter 8, we're going to introduce a concept called confidence intervals, where instead of having a single number that represents mu, we'll have a range of values. Okay, so it's going to be a little bit messier, but on the other hand, the calculators will give us a lot of help. So when that's done, then we're done with all the new material. And then as long as your assignments are done by the evening of the 27th, all that remains is that sounds right. Yes, there's August 2, I believe, is the final date of this class, although I'll double check that. And the final, I'm going to post it very soon, and it will be due in the last night of the class. So you'll have time to work on it, but it's going to cover 5 through 8. In other words, everything we've done in the last few sessions. And then we'll be done. Okay, so we're getting very close to the end. All that remains is one more chapter and then the final exam, and that should do it. All right, so congratulations. You've survived a very intense class that normally takes 16 weeks. And even then, many people find it very challenging. So yeah, you got a lot done. So your schedule should be a little lighter this fall as a result. And if you're taking stats 2 in the fall, well, you'll have everything fresh in your memories, which the other people in the class will have to remind themselves how a lot of this stuff works. So anyway, so I'll see you in the next session.